Welcome to today's webinar. The topic today is steel structure analysis in RFEM 6 and RSTAB 9. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, German and English webinars, newsletters, and so on. I will be the moderator today. My colleague Oliver Metzges will do the presentation, and Lucas will help with answering your questions. Yeah, but my two colleagues can introduce themselves.
Yes, hello. Also from my side, my name is Oliver Metzges. Here at Dlubal, I'm working as a product and customer support engineer, mainly for steel design.
Yes, hello. Also from my side, my name is Lucas. I'm also hired as product and customer support engineer. And yeah, as Andreas said, I will help him with the answers today.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. I say some words how you can ask questions. You can show or hide the control panel with that arrow here. You will find the control panel on the right side of your screen. You can ask a question here in that field, and we will answer you. If you don't get an answer during the webinar, because there are too many, then you will get an email after the webinar. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, Oliver starts with the modeling of that truss bridge here. Then he will input loads and do the combinatorics. Then follows the determination of buckling lengths with an eigenvalue analysis using structure stability add-on. And then the last point is the design according to Eurocode 3 with the add-on steel design. Okay, then I will hand over the screen to Oliver, and he can start with his presentation.
We can't hear you, Oliver.
We can't hear you.
You are sorry, muted? Sorry. Okay, I think now it works. Okay, sorry.
Yeah.
Okay, so I shortly want to show the structure that we want to model and analyze today. So it would be this truss bridge, for example, used in industrial structures for cables, pipes, or also for walkways. And the interesting topic here for this structure would be the determination of the buckling length of the top chord, because there's no lateral connection at the top. So we want to analyze this using the structural stability add-on. Okay, so we want to start with a new file. So let's create a new one. So we use the symbol for the new model, and let's call it truss bridge. And I want to directly also activate the add-ons that we want to use. So we can find them here in the add-ons tab. So as I have said, we want to use the structure stability add-on and also then the steel design add-on. Also, the next tab is interesting because we also can directly define the standards that we want to use. So we want to use today steel design according to Eurocode 3. So also Eurocode 3 needs to be activated here. And then we can also choose the national annexes, which is later important also for partial safety factors and other values in the design. So for now, I want to use the European recommendation for this webinar today. Okay, I have set my add-ons and also my standards, and then I can begin with the structure. And at first, I want to start by defining all the materials and all the sections that I want to use. I could also do it during modeling, but today I want to show how we can first define all the sections and use them later in the modeling. So I want to start with a very empty file, so I will delete all the materials and sections that have been created automatically, just by right-clicking here on the entry in the data navigator and delete all the materials and all the sections. If we now want to start by creating sections, we can do so by right-clicking here on the sections and on new section. And then this new section dialog opens. there we have in the title this option to use the section library for import of our sections. So I click on that symbol and we see, okay, in the section library, we have lots of shapes, also different types. So standardized sections, thin wall sections, also some shapes for massive sections. And today we want to use standardized sections. So the top chord, for example, and also the bottom chord should be HEB sections. So I will first go to this I section button here. And in the list, I can see that now we have all the possible I sections from different standards. So we have also American standards, for example, European standards. And yeah, at first it's a very huge list, but to find your section, you can also use this filter function here. So for example, for the region, we can input, okay, we are in European Union, and now already the list is shorter, and now it's easier to find the corresponding section that we want to use. So for example, here, the HEB section, and it should be HEB 140 in our example. Then we also have to choose a material. It's on the right lower corner, create a new material, and also here we have this button for the material library. It works a bit similar to the section library. So by default, if there's no filter active, I will deactivate this one. Then you also have this huge list with all material types, steel, timber, and so on. But by using the filters, for example, for region or material type, then you can easily find the material that you are looking for. So in my case, I want to have the steel material, and I know that it's defined in Eurocode 3. So I can also directly go here in the list for EN 1993 and find so my steel material. So I want to use the steel S355, and so I can select it here. Okay, by clicking on OK, this section is created. So I have my first section, HEB 140, and that I can easily find it later. I can also add a comment. So let's say that is the section I want to use for the chords of my truss bridge. The next section that I want to create is now a section for the verticals, so for the vertical members. And I can go again into the section library, for example, and it should now be an HEA section. So let's go again to the I sections. And if I want to avoid that, I will always have to open this list. So now I want to have those sections here. I can also add them to my favorites. So if, for example, I often have to use HEB, HEA, IPE sections, then I can also add them here to my favorite list so that I don't have to use this big section library every time. So I select all those sections by pressing Shift. And with this button, I can add them to the favorites, so my sections. I will click this. And now I can also use this library, but by clicking on the My Sections, I'm directly in those sections that I have saved here. So I can easily choose now this HEA section here. Okay, and that would be now the section for my verticals. And I want to create a new section, but it would be the same one. So I just copy it here by clicking this copy button. Now for diagonals. Okay, the next section that I want to create is for my cross beams. I create a new one. And now instead of going into section library or my sections, I can also directly type in the section name. So if I type in a section name that is recognized in the database, then it will automatically create the section. So for example, now I want to use an IPE 100. So I can directly enter IPE 100 and it will choose the first corresponding shape. So now I have here created this IPE 100 for the cross beams. So I can also add this comment here. Okay, I would need two more sections. So one now for my tension members. It would be an L shape. So I will go here in the angles and look for a corresponding one. So I want to have a small one. So let's say we can just use this section here. Okay, and the last section we want to create is for the end frames. So we will have end frames at beginning and the end of the structure. And now we want to use HEB 200 sections. So I directly type them in and it's automatically recognized and we have created this section. Okay, just add the comment for the end frames. Good, so now we have created materials and sections using section library or directly input. So now we have all our sections and we can begin with the modeling. The first fact that we want to look at is the definition of this grid in the background, because we can use these points also for modeling. So as we know now, we have seen the structure that we want to model is this structure with a span of 18 meters and the middle here at 9 meters and verticals every 1.5 meters. So it would be good to have our grid in the background also with this distance of 1.5 meters and a line, for example, here after 9 meters. So we can also define that. I will go back to the model that we are creating, this one, and we can use the symbol, for example, here for the definition and the settings of the line grid and the work plane. So this is called the work plane with all the grid points. And here we can also define the distances between the grid points. So as I have said, we want to use 1.5 meters and we want to have a grid line every 6 points. So that would be in the middle after 9 points and also at the end. Okay, now it's automatically adapted and we can use those points for modeling. So if you create now the first chord, we will go here on this button, new single member. And here we can choose the member type. It would be a beam member type and also the section. So automatically the first section of the list is chosen. So that is okay now for the chords. So HGB 140, and we simply click on OK, and then we can model it graphically. So we start here at the point 0, and then we use this grid point here after 2 lines, and we see already at the cursor the info says it's 18 meters. So exactly the length that we want to have. So I click here again, and then we have already modeled our first chord member. Now I want to also have these vertical members here. For that, I can use the division function for this member. So I right click on the member, and then I go into divide member and n intermediate nodes. So in this case, I want to have 12 sections. So I know that I would need 11 intermediate nodes. I put in 11 nodes and click OK. And now those 11 nodes are created. So every 1.5 meters, we can also hover over the members, and the info says us that the length is exactly 1.5 meters. Okay. Now I have created this division nodes, and I can, for example, now use the copy function to create the second chord member and also all the vertical beams. So I will select this all those members, and then I use the copy function. So you can find it here, the move copy functions. I click on this button, and we want to create a copy of this member, and it should be in the negative z directions 1.5 meters. Okay, so 1.5 meters in the negative z directions. If we go now under the Options tab, then we can also use this function of step links. So if you click on that, that would mean that automatically all the nodes that are created are now linked with a member. And for that member, we can choose a template. So I will create a new one here, a new member template, and it should be not a beam member, but we want to use truss members for the verticals and also the diagonals. So the truss member type says that automatically at the beginning and the end of the member, we have automatically created a hinge, so that bending moments are not transmitted at the member ends. So basically that's what I want to use for truss members. That would be the general assumptions, that I have hinges in all the nodes. So I use truss member type here, and as a section, I would use now the section for the vertical members. I say OK. And now if I also confirm this move copy function, then my chord member is copied 1.5 meters, and in between automatically all the vertical members are also created. Okay, fine. Now I would also need the diagonal members, and I want to create them in a way that they mostly get tension. So I want to start here at the upper point and go to the right lower point. So I create a new member by using this new member function. Again, it should be a truss member. So I select the truss member type, and as a section, I use now the section for the diagonals. Okay, and now I can click at the two nodes to create this member. So now, for example, I could also use again those move copy functions here to create the other members, or another method would be to use the drag and drop function. So I can simply pick this member and move it around by holding my left mouse button. And if I press the control key, additionally, you see there's a little plus symbol. And if I then go to the next node and release the mouse button, then it's automatically copied. And I can do that not only with one member, but also with multiple members. So I can also copy those two members. And if I copy them again, I've already modeled half of the diagonals. So now, as the half structure is done, I can also select all those diagonals and just mirror them to the other side. So I use the mirror function here at the top. So it's this button, and I want to create a copy, and I have to specify the mirroring plane. It would be the YZ plane, and the middle point would be one point here in the middle. Okay, I confirm it, and then all the other diagonals are created. Okay, good. So already I have half of my structure here. And now I want to copy it again to have the second half, and I will do it again by using drag and drop, because I know that the grid points in this direction are spaced every 1 meter. So as I want to have 2 meters of width, I can simply pick it again, use the second grid point here, and pressing Control key, then I can release it and it's copied again. Okay, so now I have my two truss girders here, and I need now the modeling of the cross beams in between. So I will again choose this function for creating a new member. I will leave the member type as beam, but for the cross beams, I also want to use member hinges at start and end. So the other way of using truss members, for example, would be to use beam members, but using member hinges. I want to shortly show how that works. So I have to activate the hinges function, and then there's this tab for the hinges, and I can create new member hinges that I will use at the beginning and at the end of the members. So now I want to create a new one by clicking this button. And now for the member hinges, it is like that everything that is activated, that will be released. So now it's the bending moment in Y and Z direction, so exactly what I want. So I can directly confirm this default input. And I want to have it at the member start and also at the member end. So, okay. I have to choose the correct section, I see. So this is still the first section, but I want to have the section for the cross beams, so the IPE sections. I confirm it, and now I can model here this beam by picking the two nodes. Okay, now I have created one, and I would have to copy it here 11 times so that I have 11 cross beams, and I can use again the copy function for that. But now saying that I don't want to have one step, but I want to have 10 steps. 10, sorry. And for the displacement vector, I could also put it in directly. So in the X direction, it would be 1.5 meters. But another option would be to use this picking function to pick the distance and the displacement vector directly from the model. I will show that. So I use this function, and I want to say this member should be copied from here to here. So the 1.5 meters in the X directions. In the options, I will deactivate this linking function and confirm it. And then all my cross beams are created because it's copied here 10 times. Okay, so now I also have the cross beams created. And what is missing now is here the end frame that needs to be at the beginning and the end of my truss bridge. So I want to have another member in between here. It should be a beam member without hinges. And as sections, I want to use now the section for the end frames. Okay, so from this point to that point, we have already seen this function. And now also those two members that have been created automatically, I want to modify them. So those two, and also at the other edge, I can do it simultaneously. So I select all the 4 members by pressing Control key. I can edit them by right-clicking and then choosing Edit Members. So now I can say it's no longer a member type truss, but I want to have it as a beam. And the section should also be now the one for the end frames. And as I want to use the strong axis also in the direction that I want to have this frame, I can choose also the rotation angle to be 90 degrees. Okay, so now it's rotated and the section is changed. I also have done it here at the other side, and I simply need to copy again this member by using drag and drop in this case. Okay, so I have created all the members of the truss bridge, and I see only the tension members here in between are missing. So I also create them again by using the create member function. Now I want to choose the member type tension member. So if it would get compression during the calculation, then it's removed, and the next iteration will begin without this member. So it will fail in compression. That is the tension member type. I choose the section for the tension members. Okay, and I create those two members here. And I can copy them again by using the move copy function 11 times in the X direction. Oh, that was just one time. Okay, I have removed this number, so now it's 10 times, I think. Yeah, okay. So now I have also created all the tension members. Fine, so basically the structure is created. I now just need some nodal supports. So I want to create the supports here at these 4 nodes. So I use nodal support for that. There's the button here at the top, and I will create the nodal supports type. If I create a new nodal support type, then every checkbox that is active, that will be supported. So for the first node here, I want to support all translational directions, so X, Y, and Z direction. Okay. And I confirm this choice and click on this node, and then the nodal support will be placed. Okay, I will create a new one for this node. So now I only want the Z and the X direction supported. So I activate that. Okay, for this node. And then for the other side, I also want to have nodal supports. So I create new ones. Now it should not be supported in the X direction. So only Z direction and Y direction. So I choose only that two. That would be the support type here for this node. And the other node should be only in Z direction. So I will just create this. Okay, so now we also have supports and the structure is modeled. So I can simply save it, for example. And it's always a good idea. And if you save it the first time, then you also have to specify where you want to save it. So I just save it here in my default folder. Okay, and then when the structure is saved, then we don't have this little star here anymore, because that star tells you that something has been modified after saving. Okay, now we have modeled our structure and we want to begin by creating now the load cases and also the loads. If you want to go into the load case menu, you can do so here by clicking this button that would edit one load case, and you are in this dialog for load cases and combinations. Automatically, the first load case has been created, so it's the self-weight load case, and the self-weight of all the members is automatically taken into account by using the self-weight factor. So in the positive Z direction, as it goes downwards, you have this factor of 1.0, so the self-weight is considered within this load case number 1. I also want to create other load cases. So in my example, I first want to create all the load cases, create all the combinations, and later I want to also insert then the loadings. So first we want to go through this dialog and create all load cases and combinations. What we want to have as load cases is now a second load case with the action category permanent imposed, because what I want to have here is that there's a cable load, so there are cables on the bridges on the left side. So I want to name it cable left, and it would be of this action category permanent, but imposed because it's not necessarily there. So like a live load, but not of live load action category. So that would be my load case number 2. And I also want to have another one that I also have cables at the right side, which would be additionally. So I want to say that I only can have cables on the right side if I already have them on the left side, because otherwise, if I don't have them on the right side, I want to have another load case, which would be a walkway. So if there are no cables at the right side, you can also walk at this side. So just to have some alternative that we can see how we can handle them later in the combinatorics. So the walkway, that would be of an action category of the live loads. So I will just choose one here, this action category. And the action category defines also the combination factors and the partial safety factors that will be used later. Okay, so now I have also my load case number 4 for the walkway, and I will create another one, which would be a wind load. So I create this wind load case, and I only want to have wind in the positive Y direction and also in the negative Y direction. So copy it by clicking this copy button and modify the name, so it would be negative Y direction. So that would be the load case that I want to analyze in this structure. So I don't have, for example, temperature lows to simplify it a bit, but also in my structure, as I have modeled the supports this way, also a temperature load, it would just increase the length, but there would be no internal force from that if I have this uniform temperature load, for example. So I would say for now, that is okay to have this simple structure of load cases. And we now want to perform the combinatorics by using this combination wizard. So if you go into the base tab, you see I have the combination wizard active. That would mean that I can create all the load combinations automatically. If we want to do so, we can have a look at this actions tab here, which now lists all our actions that we have, and we can choose if the load cases within one action category are acting simultaneously or could act simultaneously, or if they are, for example, alternatively. So for all the others, we only have a few load cases. So for this action category 2, we have said, okay, the 2 cable loads can also act simultaneously. But for example, for the wind loads, as I have positive Y direction and negative Y direction, it would be an alternative loading. So I can choose it here. What I can't choose here now is that the load cases also have dependencies between the action categories. So I wanted to say that the walkway can only be there if I don't have the cable loading at the right side, for example. That I can also input in the next tab, so for the design situations. Basically, in this list, I now have all the different design situations that I could analyze, and design situations are defined by the design situation tab. And as you can see, the first design situation for the ULS design also includes the formula using partial safety factors and combination values. So you can see the combination rule if you click here on this little info button, and then you see what is inside this design situation type. In this example, I only need ULS and SLS characteristics, so I can simply delete the other 2 types that have been created automatically. I will delete them. And for the first design situation type, I now want to say that I have this dependencies between the load cases. And that can be done by using this function for consider inclusive or exclusive load cases. If I create a new relationship between the load cases, then I can, for example, say, okay, my cable load on the right side, I will select the load case here, can only be there if I already have cables on the left side. So only combine it with the load case number 2. There shouldn't be the case when I have only load case 3, for example. So that was one of the dependencies that I have mentioned before that I want to apply here in the structure. And in the exclusive load cases, for example, I can then say I should never combine the walkway load, so load case number 4, with the cable load on the right side, because I've said they cannot be acting together, because if there are cables, you can't walk, and if you're walking, well, there are no cables. So that is the dependency that I want to put in here. So that can be done by using this relationship between the load cases. So I have created this dependency, and now the other rules for combination are specified in the combination wizard here. So if you click on this button to edit the combination wizard, then we can say, okay, we want to use load combinations, and the calculation should be done according to first order analysis, and I want to use stability analysis, because that is what I want to show later, that I want to use first order analysis and determine the buckling length with the structure stability add-on, so that I can later use them for the steel design using the equivalent member method. So that would be the setting for that. I don't need imperfection cases here, just load combinations and the stability analysis option. Okay. For the SLS design situation, I use another combination wizard. So I create a new one here, and in this one, I don't choose the stability analysis option because I only need it then for my ULS configuration and not for the SLS design. So first order without stability analysis here. And I also want to consider these rules between the load cases. So I also activate this option here. I can now click on the next tab, so the action combinations. So I see all the different combinations between the actions, and resulting from that list, the load combinations are created. So if I click on the next tab, I see I have 19 possible combinations of loadings with the partial safety factors and combination values. For all those load combinations, this option calculate critical load is also active because I have chosen it in the combination wizard. Okay. For now, all those combinations are empty because I don't have defined the loadings. So I will just go into my load case, and I will start with load case number 2. And now I want to define those cable loads. For that, I want to use the load wizard. So I want to use the load wizard member loads from area loads here. And for that, I need some help nodes in my structure, because I want to say on the left side, I only have this cable loading, and I use the member division function to create a new node on this member here, defining the left side of my bridge. So I right click on those two members and use this divide member functions, now with a distance. And I want to say from the member end, I want to divide it at the place of 40% of the member length. And here I also want to activate this option, create on member nodes without dividing the member, because I want to still consider this member as one member later for the design. It's only a help node that I want to place here. So I use this create on member nodes function. Okay, and now the left side for the cables is specified here by this 40% of these nodes. Now I can use this member load wizard, member loads from area loads. I right click on it and create a new load wizard. And in my example, I want to say I have 1.5 kilonewton per square meter in the Z direction. And for the geometry, I can now select those nodes that I have created. So I use this picking function here and select the corner nodes of my surface load. So this one, the help node, the other one, and that node. So I want to place a surface load on this plane. Okay. And in the background, you already see selected all the members that will be loaded. So I see the load will be distributed to the cross beams, but also to the chords. And I want to remove now the load from the chords. It should all be on the cross beams. So I can use this function and select all members that are parallel to one of the chord member. Okay. And now we see only the cross beams will be loaded. I confirm it. Okay. And now we see this load as a surface load, and we can also display it separately. So if we right click on it, we have this function display separately, and we see, okay, from the surface load, automatically these member loads are created on the cross beams. Okay, and we can again right click on it to see it as a surface load. So that would be the load case for the cable load on the left side. For the right side, I want to use a different load wizard, but again with help nodes. So I will again divide those members. So right click on it, divide member by a distance. And now it should be in the middle, 30% from the start and on member nodes. Okay, and now I want to place, just to show you another load wizard, the member loads from a free line load. So I want to assume there's a line load, and from that I want to create the member loads. So for the cables on the right side, I create this new load wizard here. And let's say we have here 1 kilonewton per meter, and it should go from node to node. So I use this button here to select the two nodes. It should be this one and that one. And now we don't need to exclude any members, as only the cross beams will be loaded. So it would be okay now. I confirm it directly. And you see, okay, I have placed this line load here. And as it was for the surface loads, I can also right click on it, display it separately, and you see, okay, those point loads will be created from this load wizard. So it's just another load wizard that you can use. So I use it now for the cable load on the right side. Okay, for the walkway load, I will use again the member loads from area load. So I can create a new one. And now I want to have 3 kilonewton per square meter. And again, I want to pick the nodes here, now the other side. And I click on all the nodes. Oh, I see I've not picked this one. Okay, now I have them. Okay, and remove the influence again from all the members that are parallel to this one. Okay, I have here my surface load. Oh, it's 30. I added it again because I wanted to have 3. Yeah, that is better. And I could also display it separately to check the load. Okay. So now the missing load cases are now the wind load cases. And for the wind load here, I also want to again use this member loads from area loads function. But as I have a structure with openings, then I would also I would calculate the wind load value also by using a fullness coefficient. So at first I will use the parameter function here. So in the table for the structure, you have also this button for edit the global parameters. And then you can define parameters that you use in your model. Also for parameterization, for example, of the height or the width, it would be possible. Now I only want to use it for the calculation of the wind load. So let's say we have a wind pressure here, and we simply insert it here. So it would be a load. So we have it here as a surface load, this 1 kilonewton per square meter. And for the wind zone that I'm in, I have here 0.4. I would also have to consider a force coefficient. So because I have the section shapes here and a truss beam, so that would be a coefficient. So I have it as, let's just use this partial factor because it would be the same from the units. So let's say it's 2 in this case, and the fullness coefficient. So we have phi. I will use again this this partial factor type. Okay, and now let's say we have a fullness coefficient of 0.2. Now, as we have defined all those values here in the global parameters dialog, we can also use them later in our model. So I've defined my parameters here. I confirm it. And now I can create the new load wizard. So for the area loading, and it would be now in the y direction. So y direction and the load magnitude, I can calculate it using the parameters. I click on this small button here on the right side and choose the edit formula option. And now I can say, okay, it would be now a QP times force coefficient times fullness coefficient. So that would be my value that I want to place on the surface, and it will also be distributed on each member. Okay, so I use that here, and the geometry would now be this this side. So I choose here the corner nodes, And I also say, okay, I also have a second load plane on the other side. So I don't want to consider now the shading, for example, for simplifying the model. I just want to place the same loading on both sides. And I can confirm it. So I want to have here my wind load on both sides. And I also want to have it in the next load case, but now in the opposite direction. So I can, for example, also copy the loading by going into the load case dialog and using this button here at the bottom to add the loads from an existing load case to another one. So I go to load case number 5, use this button, and I want to copy the loads into the existing load case number 6. Okay. And now in load case number 6, I also have this loading, and I want to have it in the opposite direction. So I go inside and I edit the formula again by adding a minus. Okay, and now it's in the opposite direction. Good, so now we have also all our loadings inside. So all the combinations will already have the correct loading inside. And now we could, for example, calculate our design situation number 1. And this design situation number 1 includes all the results from all the load combinations. And as I have selected the stability analysis option, it performs first static analysis and then also stability analysis by using the internal forces from the static analysis as a basis. Okay, so now I have my results. And as I have said, in this design situation number 1, there are all the results included. So I can show max and min values. So for example, if I go into this result navigator for the members, I can show internal forces. So normal force, and it would be max and min values here. And to have it a bit more clear in the view, I don't want to show all the beams, but maybe just the chords. And so I can use visibility options. So I select here my 2 top chords, for example, and then use this button to create a new visibility by the selected objects. Now I can see, okay, I only have now these 2 chords in the view. So I see, as here are max and min values, I will always have compression in this chords, well, as expected, as it's a simple beam as basic structure. So I have compression in the top chord, tension in the lower chord. And then I would also have tension in diagonals and compression in the verticals. So the highest compression force here, 150 kilonewton, and it's a varying compression force. So it's lower at the end and higher in the middle. Well, basically as I have expected. And like that, I could also show all the different results, also deformations, for example. Yeah, so that is this result navigator function here. Okay, so now we have created the combinations, we have modeled the structure, and now the next point that we want to look at is the determination now of the buckling length, because that would be the interesting point here. For my top girder, as I don't have here lateral restraints, I'm interested in the buckling length of this top girder. So we have now performed stability analysis, and we have performed it for every load combination in the design situation number 1. As a summary result, we also get in the summary table from design situation number 1 the minimum critical load factor from the stability analysis. And now we see it's 0.4 in combination 8. So now we can also have a look at combination 8. So I selected here in the list, combination 8, and that would be the mode shape. We can display everything again, but to see it a bit better, we can also change the display option for the deformation. So in the result navigator for deformations, I change it from members to colored sections. Okay, so now we see the governing mode shape would be this buckling shape of the top chords. So we have said, okay, we have no lateral restraint here. We have assumed all those vertical and diagonal members with hinges at the ends. So basically, I don't have any any restraints in the middle. So it would be this one wave buckling shape for these members. And as I see, we are at a factor of 0.4 approximately. So That would mean that with the given loading and the modeling that we have chosen, that would be unstable, the structure. So if, for example, we would calculate it using second order analysis, we would get a message that it's unstable because the critical load factor was lower than 1. So in the current state, we can't design the structure. That would not be sufficient, but we can now think of ways how we can enlarge the load factor and also the buckling resistance of this member. So what would definitely be good in this case would be to create another frame, just like the end frame, here in the middle of the structure. So in my example, I want to create in this middle here another frame that can hold this top chord here. So for that, I want to choose the member type of those two vertical members. So I select them, right click on them, edit members, and it should now be a beam member type. And I also want to rotate the section here about 90 degrees to use the strong axis bending moment for that. Okay, I confirm it. And also for this cross beam, in this case, I also need to remove the hinges because I want to have this this frame to be developed here in the middle. So I remove also the hinges, and now I see that I also have forgotten to place hinges here at beginning and the end of my chords. So that was the intention, because I also want to assume that they are hinged here at the beginning and the end. So I will simply add the hinges again. So I also select those members, create the hinges again at the member start. Okay, so I have forgotten it during modeling, but I can easily add them now. So I select those members, and now it would be at the end. So I go on hinges again and place the member hinge at the member end. Okay, so I have the hinges here, but the important change now was the insertion here of this frame in the middle. And if we now look again, for example, at this combination 8, or we can calculate design situation number 1 again, so then you see it again, static analysis for all those 19 combinations and also stability analysis for all the combinations. And now we see the result. Now the governing load combination would be combination number 9, but the minimum critical load factor is now 1.2. So if you now look at combination number 9, and here we can switch to stability analysis, then we see, okay, just because of creating this frame in the middle, so it is stiff enough that we now don't have this one wave buckling shape, but now the top chord is forced to create this 2-wave buckling shape. So that is already good. And so now we are at a critical load factor of 1.2. So now it would be also stable, for example, if you calculate it according to second order theory. And that was already this change of creating the frame here in the middle. Now, the structure stability add-on is not only able to calculate critical load factors, but we can also calculate buckling lengths. So in the result table, we can, for example, choose the results by members. And I want to use a visibility again to filter the results a bit. So I select again all the top chord members that we are interested in now and use this visibility by selected options function. And we can have a look now, not into the mode shapes tab, but into the table for effective lengths and critical loads by mode shape. So for mode shape number 1, we get now effective lengths and critical loads for all the members that we have here. So the first thing that we can see is that for the results, we always get 2 effective length values, so L critical U and L critical V. Basically, that always means that it's flexural buckling about this axis, so about U axis or about V axis, and U and V, that are the principal axis of the structure of the section. So for doubly symmetric cross sections, they are identically to Y and Z axis. So we can also show this axis, for example, in the graphic. So if you right click on the members, we can activate the local axis system. So the direction that we are now interested in is the buckling around the z-axis. So that is the direction we want to look at, and the other values we can't use them. So basically now we can only use one of those values because it's a flexural buckling around the z-axis. And if you are not sure which of those you have to look at it, so it's around z. If you have, for example, unsymmetrical cross sections, then you can simply look at it. So in the sections, we can have a look at the L section. Then we see, okay, the u-axis belongs to the y, and v, that would be the equivalent to the z-axis. So if we have a doubly symmetric cross section, for example, because then it's not shown like this. So now we want to have a look at this L critical v, because that would be the result that we are interested in for this buckling shape. So that's the first point. So we need to look at this value and not at this value. The second point would be that we can see we now get different effective lengths for every member here. So basically that is because of the varying compression force in the top chord. So we don't have a constant compression force here in this case. If you would have a constant compression force here, we would get the same effective length for all the members, and probably this effective length would also be 9 meters because, well, it's the length of one of this. It would be the half length of this of the whole length. So to the middle we have 9 meters, and as we have the buckling length here at this distance, it would also be 9 meters. Now we have this varying compression force, so we get different values for all the members, and it's this value of effective length is always matching with the critical load. So basically the structure stability add-on calculates critical load factors, and then by using this factor and the actual compression force in each member, we can calculate a critical load for each member. And based on this critical load, which is lower if we have a lower compression force and higher if we have a higher compression force, based on this critical load, we calculate the effective length. So basically, for example, the formula for calculating critical load is using the effective length, also later in the steel design add-on. So this is just a turnaround. So we have the critical load and we calculate the effective length that I would need to insert in the formula to get this critical load. So basically for each member, I would have now the corresponding critical load and corresponding effective length. For the design checks later, I would use this effective length of the member with the highest compression force, because that would be the most governing design check. So in this case, it would be the effective length of 7.7 meters. It is lower than the 9 meters because we have a positive effect that we don't have a constant compression force, but it's a varying compression force. So it is lower than 9 meters. That is as expected. But we don't want to, or we can't use the biggest value because it's only corresponding for this member. For the member with the highest compression force, we can't use this one. It would be on the very safe side to use the biggest one, but it would be good to always use the one that corresponds to the compression force of the member. Okay, and for example, I could use then in the design always this effective length for each member. So I could create effective lengths for each member that is equally loaded and use all of those effective lengths. Or the possibility that I want to use, I use this effective length of the member with the highest compression force for all the members. In the results later, I will shortly show some pictures. There's not a big difference. So that would be the result if I use the same buckling length for all the members. So now it's the length from this middle member, so the 7.7 meters. If I use always the corresponding buckling length, then it would be a smoother distribution. So now I am a bit on this unsafe side for the outer beams, but as the most governing design check is in the middle, and I use the same cross section for the whole member, which is also the basis for the equivalent member method. So it is okay in my case just to use this effective length from the members with the highest compression force. Okay, so now I use it here. I close those images. Okay. Now I want to show how we can define the buckling lengths in the steel design add-on. So we have here these types for steel design, and there are effective lengths, boundary conditions, and also all the members have now settings for steel design because we have activated the steel design add-on already in the beginning. So now I want to set up those effective lengths. So I create here a new effective lengths object, and that effective lengths object is used in steel design for the equivalent member method. As I have performed the stability analysis, I can use this option for the import of effective lengths from stability analysis. So I can go into this tab, import from stability analysis, and for my top chord members, I want to import it from my combination number 9 and the first mode shape. So it's the one that we see here. And I have said from the member with the highest compression force, so this one. And I have this effective length factors automatically inserted for the direction around the z-axis. And for the other direction, I have 1.0 here as effective length factor. Okay, now I have to assign this to all my members of the top chord. So I cancel the visibility mode, and I can also, I can select now all the top chord members here. And now this buckling length imported from stability analysis will be assigned to all the members here. Okay, I will just turn off this display of the local axis system and also of the results. So that would be the input of the effective lengths for the top chord members. And I can also do so for all the other members. So I will create a new effective lengths object. Now it should be for the diagonals and also for the verticals. And here I can also go directly into the node supports and effective lengths tabs because I don't want to import it from stability analysis. And here basically the effective length factors can be set. So I want to use 1.0 in the direction out of the truss member, and I could use, for example, 0.9 for the buckling in the plane of the truss member. So I can set the factors also directly. So those settings by nodal supports, they are used for lateral torsional buckling. If, for example, I have intermediate nodes, I can create also a segmentation and set lateral supports. In my case, I just want to assume, start and end fixed and also with the torsional restraint. So this default setting is okay here, and I assign it here to all my vertical and diagonal members. I don't set it here to the frame members because we can maybe think of them a bit more detailed. So just the standard diagonals and verticals. Okay. For this frame members, we could also set this effective length, but it would be a bit more complicated for the buckling in the plane of the frame, because the frames could also have buckling factors, for example, of 3 or 4, and we don't have this lateral restraint at the top because, well, basically this frame is the lateral restraint of the whole structure. So I would not set a lateral support here at the top. But we could also calculate this effective length factor by using stability analysis. If we would do so, we would find critical load factors around 40, for example. So if I would perform stability analysis and look at mode shapes where the frames have a buckling in frame directions, it would be higher than 40. So in this case, the flexural buckling about the strong axis is not relevant. So I just skipped the part of calculation of the critical load factor and effective length factor because it's not relevant here. I can also directly deactivate it here in the effective length setting. And for the others, I could also use the factor of 1.0 for the weak axis bending. And for lateral torsional buckling, I want to assume that at the top, I don't have a torsional restraint. So I say it's only at the start of the member, but not at the member end. You will see that it's not governing for this end frames as they are not heavily loaded, but just to show you a bit of the input options that we have here. Okay, now I have to assign it also to the frame members. Okay. So the input of the effective length is now done. We also have this cross beams here, which mainly have a bending moment. So we need to check lateral torsional buckling. We could also do it by using effective length and then setting up the nodal supports. That would also be possible. So effective length always means we use the equivalent member method. And we also have another method implemented, the general method. And that could be defined by using boundary conditions. So if you want to use equivalent member method, you set up effective length. If you want to set up the general method, then you use boundary conditions. So I just want to show how that works. I create a new boundary condition. And basically, yeah, it's done by nodal supports. So we have this tab of nodal supports. And there we just set up the boundary conditions that are then used in the eigenvalue solver. So we use an eigenvalue solver using the beam with the nodal supports that we put in here and the internal force from the main analysis. So in my case, for the cross beams, I want to say I have the forked support at the beginning, at the end. So already this default setting is okay for me. I don't have any intermediate lateral restraints, so I don't need intermediate nodes or something. I can simply use also this default setting here. Now I need to assign it to all my cross beams, and for that I use a filter function that we can find here in the display navigator, and we use visibilities of members by sections, so activated for the cross beams only. So and then I can select them all, and I would also need it here for the end beams, so this one and that one. Okay, so now also the boundary conditions are set up. So, and that would already be the input for my ULS design. I also have created a design situation for SLS design, and I can also use the members for serviceability limit state. In my case, I don't want to check the deformation of all the members. It would only make sense to check the deformation at some places for the whole structure. So in this case, it would be the vertical deflection of the whole bridge. So for that, I could, for example, use a member set of the bottom chord, or I could also use a single member. So if I use these two single members, for example, and right click on them, then we see, as I have activated steel design, all the members that are designed have this option for design supports and deflection. And there we can say the direction that should be checked, and also the length that is taken as reference length. So as I want to check, yeah, this member is equivalent to the whole structure, I can also activate it here, the user defined length, and define it with 18 meters. In this case, it's already recognized as the whole length. So that would be okay. So if I define, for example, then I want to check as a limit L to 200, then it would take the 18 meters as reference length. These limit values are defined in the design configurations of the serviceability. So we have here the serviceability design configurations. And if I click on that, we see we can enter the deflection limits here. So for example, if I want to check L per 200, I can input it here. And then this limit is set, taking the reference length of this design support and deflection tab. Now I have said I don't want to check all the members for serviceability, but only those two. So I can also assign this serviceability configuration not to all the members, but only to those two members. Oh, that's wrong. I want to have this one and that one. Okay. And confirm it. Confirm it again here. Now I see that, for example, this member in the design configurations tab doesn't have a serviceability configuration assigned. And all the objects that don't have configurations for a certain limit state will not be checked in this limit state. So a member without a serviceability configuration will not be checked in serviceability limit state because there's no configuration assigned. So also, for example, in ultimate limit state, if you don't want to check this member, you can simply unassign the configuration. But by default, configurations are always assigned. So you won't, there's no member that you can forget because they will have configurations by default also. Okay, so now only one thing left, so we can calculate the steel design. So we go into the table for the steel design. We have here our input data. You see objects to design, materials, sections, so everything like we have specified before. Also ultimate configurations and serviceability configurations. And for the ultimate configurations, we can have a look at them. So if you double click on this line, then we see that we have chosen here to perform the stability design. So we will take into account effective lengths and boundary conditions that we have set up for all the members. If we don't want to perform stability design, so let's say in our example for the bottom chords, we know they have only tension force, so we don't need stability design. We could also do so by assigning another ultimate configuration. So let's say we create another one and we uncheck perform stability design. And we can now, for example, select all the bottom chords. So we filter them by using this visibility again. So we can assign this ultimate configuration to all the bottom chord members. So we won't check stability design here. As we have tension, it would be okay in this case. Good, and now we can calculate the steel design to see all the results. So we already have calculated the combinations from ultimate limit state. So now it will calculate serviceability limit state and then perform the steel design. So we will have a look at the results and then we are finished here with the structure. So now we get this result here. So basically we can show the envelope values and it will display a ratio for our members. So the flexural buckling design check here for the top chord would be at 1.03. I would say, well, that's quite okay in this case. And if we double click on this design check, so in the overview, we will see all the design checks that are over 1 or where there's a problem, non-designable or something. We will see it here and we can directly click on it also. So if you double click on it, then we see the design check with all its intermediate values. And also for all the design checks, the formulas are also displayed. So the buckling design check is quite a big one with lots of intermediate values. And you see here all the values. And as we can see, we said, okay, we want to specify the buckling length around the Z axis in a way that we get the critical load correctly also in the design check. So we used the 7.7 meters. And basically it calculated now the critical load of 190 kilonewton. And if, for example, we check back in the stability analysis, then we see in the member results for this member, it was the 190 kilonewton of critical load. So the result will match because we have used this effective length here. Okay, so I think that was it for the structure. We have seen the modeling, we have seen the loading, we have explained the functionality of the structure stability add-on. We determined the buckling length of the top chord, and then we set up all the input for the steel design using effective lengths, boundary conditions, and now we have also seen the results. So I think, yeah, that was it from my side, and I will give it back to Andreas.
Okay, thank you, Oliver, for this nice presentation. I hand over the screen again. I post the link already in the chat. If you want to get a deeper insight in the steel structure design, you can book our training. It's a 4-hour training. You will get compact basic knowledge. We work, or you can work by yourself on practical examples. You will get an insight in the detailed ultimate limit state design and the serviceability limit state design and so on. You will get the certificate as well. Yeah, it costs 250 euros. I think it's not too much. You will work faster after the visit of the training. Okay, here's the link. You can download the PDF from our website. I will show it where you can find it. You can also use the QR code. If you want to get an offer of our add-ons or our products, you can contact our sales team via that link or the QR code. You can also book a free product presentation, or something like that. Or you can book the training as you want. I show the website before I will close the webinar. Under dlubal.com, you find under news and events, you find the webinars. Those are the upcoming webinars. Next week, I will present the modeling and design of solid elements. And this is today's webinar. I click on it. You will get a link in the next days where you can find you will find the recording here. You can already find the presentation slides here. And also you can find the model here. You can download it for free. And you can exercise the webinar with the recording and the model as you want. Okay, that should be also all from my side. Thank you for your attention. Thanks to Lucas for answering the question, and a special thank to Oliver for the presentation. I wish all a nice rest of the day. Maybe we meet each other in another webinar. Bye-bye.